Welcome to Dreaming Scientist's Sleepy Stories, a place where the mysteries of the universe guide you toward peaceful sleep. Something quiet waits at the edge of modern physics, a tiny weight you would never notice in your hand, yet a mass so large it towers over every particle ever found. You're about to drift into the realm of the Planck mass, a number so unusual it unsettles intuition itself. So breathe softly, let your shoulders fall, and step with me into the thin place where gravity and quantum rules touch. Tonight, you wander toward a boundary Einstein and Planck could only sense and outline, a frontier that glows faintly between the known and the impossible. And as you settle into stillness, the first chapter opens. Why does this mass refuse to behave the way logic demands? The Planck mass begins as a contradiction sharp enough to make experts pause. To your everyday sense of size, it is unbelievably tiny, just 2.176 times 1080, 2.176 times 10⁻8, 2.176 10⁸ kilograms, a whisper of weight lighter than anything you'd ever feel. Yet compared with the particle's science studies, it rises like a mountain. Not even the heaviest particle in the standard model approaches it. And that delicate mismatch gives the Planck mass its strange power. To understand why this quiet number defies expectation, you have to follow how nature defines it. It does not come from atoms or molecules, but from three constants so deeply woven into reality that removing one would unravel physics itself. The gravitational constant GGG, the reduced Planck constant AH bar, and the speed of light CCC. When Max Planck brought these constants together in the late 1800s, he wasn't seeking a new mass scale. He was building a system of natural units, measures chosen by the universe, not invented by human hands. Yet the mass that emerged felt misplaced, neither the size of a particle nor the mass of a star. Even Planck didn't realize what he had uncovered. Later, as quantum mechanics took shape, physicists noticed something peculiar. This mass rested exactly at the meeting point between Einstein's smooth fabric of spacetime and the quantum world's grainy, packet-like nature of energy. Below it, quantum rules dominate. Above it, gravity takes control. Right at the Planck mass, both forces hold the same strength, neither able to be ignored. Richard Feynman once remarked that nature weaves her patterns with long threads. You can imagine the Planck mass as one of those threads, binding together quantum behavior, curvature of space-time, and the cosmic speed limit into a single quiet number. To sense how unusual it is, think of the particles you know. An electron carries a mass of only 9.11103, 119.11 times 1031, 9.11 times 1031 kilograms. A proton sits at about 1.67 times 10, 271.67 times 10, 27 1.67, 1027 kilograms. Even a tiny grain of dust doesn't come close. Yet on human scales, 10,800, 10,8, 10,8 kilograms is almost nothing. No heavier than a delicate eyelash. The Planck mass sits in a lonely middle ground, too heavy to belong to the quantum world, far too light to belong to ours. Early physicists struggled with this tension. Quantum mechanics described electrons and atoms beautifully. General relativity described planets and galaxies with equal elegance. But the Planck mass pointed toward a place where these two theories would have to confront each other, a place neither was designed to handle. It became more than a curiosity. It was a quiet warning. Near this mass, space-time trembles. Quantum fluctuations grow fierce. Gravity ceases to behave like the gentle curve, you know. And if energy equal to the Planck mass was squeezed into a region the size of the Planck length, 1.616 10 300, 51.616 times 10, 35, 1.616 times 1035 meters, a tiny black hole would bloom instantly. At this boundary, no one knows how space-time truly behaves. Einstein's equations insist on smoothness, while quantum mechanics predicts a restless, foamy texture, a term John Wheeler described as quantum foam. The Planck mass sits right at the threshold where these visions collide. The story behind its discovery adds to its charm. Planck had been trying to solve the puzzle of blackbody radiation, a mystery classical physics could not explain. His work opened the door to quantum mechanics. Years later, Einstein's relativity brought gravity into the picture, making the gravitational constant essential. With G, GG, AH, bar, and CCC together, the universe revealed a mass scale that existed long before any laboratory did. That is why the Planck mass feels like a hidden message, a clue written in the universe's own handwriting. To appreciate how strange it is, imagine holding an eyelash lightweight in your hand. On your scale, it's barely there. But if a particle carried that mass, it would be astonishingly heavy, around 101910, 191,019 gigaelectronvolts. So massive that the familiar forces of the quantum world would no longer behave in their usual way. At this point, gravity would suddenly matter, not the soft gravity you feel on Earth, but a gravity powerful enough to compete directly with quantum interactions. This is why the Planck mass marks the place where all physical laws must eventually meet. Here, a particle becomes heavy enough to noticeably warp the space around it. Even the formula that creates it tells a story. Its form essentially a square. Root of PG, HB, HB, contains none of the properties of matter, no charge or temperature or chemical behavior. It relies only on constants that define the structure of the universe. The Planck mass is not chosen. It is unavoidable. Imagine physics as a long ladder. At the bottom lie the smallest masses: electrons, neutrinos, quarks. Higher rungs hold atoms, molecules, planets, stars. Nearly everything fits comfortably on this ladder. But the Planck mass stands alone, far above the quantum rungs and far below the astronomical ones, a solitary marker placed at the border between the quantum and gravitational worlds, yet no known particle occupies it. This has led physicists to wonder whether the universe is hinting at something deeper. If this mass truly marks the point where gravity must become quantized, then this is where the standard model and general relativity finally come face to face. By the late 20th century, new theories began exploring this frontier. String theory treats the Planck scale as the natural tension of vibrating strings. Loop quantum gravity uses it to define the smallest grains of spacetime. Models of quantum foam use it to describe the restless geometry that may fill the tiniest distances. Across all these ideas, the Planck mass appears again and again, a quiet signpost pointing toward the theory that will one day unify all of physics. And for now, you can simply rest here with it, at the threshold where the universe whispers its deepest secrets, where gravity and quantum rules hold hands, and where your quiet journey into part 1 gently comes to a close. And yet, despite its immense significance, the Planck mass is not something we can measure directly. No particle accelerator on Earth can reach the required energy. Even the Large Hadron Collider, capable of pushing particles to trillions of electron volts, remains unimaginably far below the 1019 GeVC 21019. Text GeV-C to 1019 GeV-C2. Energy scale associated with the Planck mass. This places the Planck mass on a frontier we cannot cross experimentally. At least, not yet. Instead, scientists approach it indirectly through black hole physics, the early universe, and gravitational waves captured by observatories like LIGO. Each of these phenomena carries faint hints of processes near the Planck scale, the way distant echoes reveal the shape of a hidden room. That is why this one mass value, so tiny in kilograms, so colossal in electron volts, continues to command attention. It is not a number humans invented. It is a number woven into the fabric of nature itself. Somewhere inside that quiet value lies the boundary between the physics we understand and the physics waiting to be discovered. As the imbalance between these numbers settles in, something subtle pulls us forward, a sense that this strange contrast is pointing us toward the next step. When a mass appears minuscule in kilograms, yet climbs to a scale no particle can ever reach, one thought becomes impossible to ignore. Part 2. Why is a mass so small in kilograms still a million billion times heavier than any known particle? Something extraordinary happens when you stop measuring the Planck mass in kilograms. A value that once seemed tiny to 0.176 times 1080 to 0.176 times 10⁻8 to 0.176 times 10⁸. Kilograms suddenly becomes one of the largest quantities in all of particle physics. In the units physicists actually use, giga-electron-volts per C(AC) to C², the Planck mass leaps to a staggering 1.22 times 1019 GeV, C21.22 times Y19. Text GeV-C to 1.22 times 1019 GeV-C. 2. A number so enormous that it towers above every particle ever detected. This single conversion opens the door to a landscape where intuition fails. Light particles drift almost weightlessly, while the Planck mass stands like a mountain rising out of mist. To understand why this value becomes so immense, imagine how mass is measured in everyday life. Kilograms work well for apples, spacecraft, and laboratory equipment, but in particle physics, kilograms are far too coarse. The masses of electrons, quarks, and neutrinos are so small that kilograms bury their true values beneath oceans of zeros. Physicists therefore shifted to the electron volt, a unit tied to how much energy a charged particle gains in an electric field. Once Einstein showed that mass and energy are interchangeable, the electron volt became the perfect language for describing the smallest building blocks of nature. With that shift, the gap between ordinary particles and the Planck mass stretches into something surreal. An electron weighs only about 0.511 MeV-C, 20.511 text MeV-C to 0.511. MeV-C2, less than a millionth of a GeV. A down quark. Around 4.5 MeV-C, 24.5 text MeV-C to 4.5 MeV-C2. Even the top quark, the heaviest of all known particles, reaches only 172 GeV-C 2172, TeXeV-C 2172, GeV-C 2. Now compare that with the Planck mass, 1.22 times 1019, GeV-C 21.22 times Y19, TeXeV-C to 1.22 times 10, 19 GeV-C 2. The difference is overwhelming. The Planck mass is not a few times heavier, it's about 100 trillion times heavier than the top quark. Physicists often compare it to a mountain standing above a field of dust. And this imbalance raises a quiet but profound question. Why would nature create such a vast gulf? For decades, physicists believed that the Higgs field, the invisible field confirmed in 2012 at CERN, would ultimately explain all particle masses. And while the Higgs mechanism does explain why particles are not massless, it does not explain why their masses fall so far below the Planck scale. Nothing in the standard model requires electrons to be light, or quarks to stay so far beneath this towering value. This discrepancy drove theorists deeper. Why is matter so light? What prevents particles from drifting anywhere near the Planck mass? Particle accelerators like SLAC, Fermilab's, Tevatron, and CERN's LHC spent decades probing mass at high energies. Each time, the results pointed in the same direction. Particle masses barely budge, no matter how much energy we pour in. Their stability contrasts sharply with the silent enormity of the Planck scale that has never appeared in any experiment. No detector has glimpsed a particle near it. No natural process in today's universe reaches it. Even the hottest moments after the Big Bang, as inferred from the cosmic microwave background measured by COBE, WMAP, and ESAS, Planck satellite, show no evidence of such ultra-heavy matter. To understand the gap, theorists proposed ideas that span generations. String theory imagines particles as tiny vibrating strings whose tension is set by the Planck mass. In this view, ordinary particles are low-energy vibrations, while the Planck scale is the natural frequency where gravity becomes quantum. Loop quantum gravity instead pictures space itself as woven from discrete threads, with the Planck mass marking the scale where those threads twist strongly enough to produce measurable gravitational effects. Different approaches, same conclusion. The Planck mass marks the threshold where gravity and quantum mechanics must be treated together. Below it, gravity whispers. At it, gravity roars. A particle at the Planck mass would distort the space around it so intensely that if compressed to the Planck length, it could collapse into a microscopic black hole. This is not speculation, follows directly from combining quantum mechanics with Einstein's curvature of spacetime. This leads to one of theoretical physics' most haunting insights. If a particle ever reached the Planck mass, gravity would behave so violently that familiar structures could not survive. Quantum mechanics and general relativity would collide, tearing open the quantum structure of space-time itself, what John Wheeler once described as quantum foam. And so the question returns, why is all known matter so light? Some theorists propose hidden symmetries that forbid heavy masses. Others suggest that if particle masses were much larger, matter would collapse before galaxies could form, an idea supported by cosmic structure simulations from NASA and ESA. Teams studying early universe behavior, even the top quark 172, Jevon produced only in the most extreme collisions sits unimaginably far below the Planck mass. Studying it is like examining the lowest rungs of a ladder whose top remains forever. Out of reach, the Planck mass is the highest rung. The point where our equations meet the unknown. No accelerator can reach it. No star or black hole reaches it. Only the newborn universe ever touched it. That is why the Planck mass appears so unnatural. At first glance, it belongs to a domain the modern universe has long since cooled away from. Everything around us, atoms, quarks, photons, is a relic of gentler times. The Planck mass belongs to the era when the universe was young, hot, and unrecognizable. Though, enormous gulf between the Planck scale and ordinary particle masses is not an accident. It is a fossil record, a memory of how sharply the universe separates the world we inhabit from the energies that forged it. And the further these numbers stretch apart, the clearer it becomes that our familiar units were never meant for scales like this. They buckle under the weight of values spanning so many orders of magnitude. Part 3. Why did physicists stop using kilograms and switch to electron volts? Something in physics broke so completely that kilograms could no longer keep up. It wasn't a mistake, and it wasn't a trend. It was a realization so sharp that the entire field had to change the way it thought about mass. The shift began the moment scientists entered the quantum world and discovered that the smallest pieces of nature were far too light, far too subtle, and far too delicate to be described by a unit built for apples, engines, or spacecraft. Kilograms, perfect for the visible world, became clumsy giants the instant we tried to apply them to particles. The question haunting early physicists was simple. How do you weigh something so small it slips between atoms? So light it has no presence in daily life, yet so important it shapes everything. To answer that, we return to a quiet rearrangement in Physics 1, revealed by Albert Einstein in the early 20th century. He showed that mass and energy are not separate quantities, but two faces of the same physical reality. His idea that energy equals mass multiplied by the square of the speed of light does not need symbols to be understood. It simply means that a tiny amount of mass contains an enormous amount of energy. A tiny amount of energy behaves as if it has a certain mass. That realization changed everything. Once mass and energy were unified, physicists no longer needed two separate systems of measurement. They could describe both with a single unit, and that unit already existed, the electron volt. A measure of the energy gained by a charged particle moving through an electric potential. The electron volt was tiny, precise, and perfectly matched to a world where particles lived on the edge of meters. Rabilet why? To see why kilograms failed. Imagine weighing an electron in kilogram units. Its mass must be written like this: 0.911 times 10 kilograms, instead of a clean value. You get a whisper of a number so tiny it gets swallowed by leading zeros. Even the earliest researchers felt the weight of this problem. Numbers this small simply refuse to sit comfortably in the kilogram system. But when expressed in energy units, the same mass becomes 0.511 MeV c² clean. Compact, useful, that shift from impossible numbers to workable ones became essential for progress. In the mid-20th century, as particle accelerators such as the Bevatron at Lawrence Berkeley Laboratory and the proton synchrotron at CERN began smashing particles at higher and higher energies, researchers needed a unit that reflected the energies of the collisions themselves. The electron volt matched the machinery. Kilograms did not. NASA adopted electron volts when studying cosmic rays because these particles carried trillions of them. Even astrophysics followed suit. ESA continued the practice in the Planck mission, reporting early universe fluctuations in electron volts because the primordial cosmos operates naturally in energy units, not mass units. Once physicists adopted the electron volt, an entire hidden structure became visible. Quarks had masses in megaelectron volts. The Higgs boson appeared at around 125 gigaelectron volts. Neutrinos weighed less than a single electron volt, so small that only the most sensitive detectors on Earth could measure them. These detectors buried beneath mountains or sealed in silent caverns to escape. Cosmic rays relied on electron volt precision to catch the faintest signals. Kilograms could never capture this delicacy. The shift wasn't aesthetic, it was survival. Physicists needed a unit that could reflect the quantum world without collapsing under zeros and exponents. The electron volt let mass, energy, and momentum all share the same mathematical language, but the story becomes even deeper when you consider how particles actually interact. Particles don't behave like billiard balls. They exchange energy through fields, through the quantum rules that govern every force in nature. The electron volt doesn't just measure mass. It measures interaction, strength, collision, energy, temperature of cosmic plasmas, and the internal dynamics of stars. When two electrons scatter, the interaction depends on energy, not mass. When quarks bounce inside a proton, the strong force cares about energy, not kilograms. When nuclear reactions power a star, the relevant scale is millions of electron volts, not grams or kilograms. Astronomers measure the cosmic microwave background using electron volts because the early universe behaved like a quantum plasma where energy per particle is the natural language of physics. ESA's Planck satellite detected temperature variations equivalent to tens of microelectron volts tiny. Fluctuations that later seeded galaxies. Behind every milestone lies the struggle against units too large for the quantum world. Even the proton's Masar-Bawan-Jev was too small for kilograms to express cleanly. By the time particle discoveries surged through the 1960s and 1970s, the scientific community realized that the kilogram system had reached its limit. Einstein had given them a new path. The universe had given them a new scale. The electron volt became the key that unlocked the quantum world. Carl Sagan once said, "We are a way for the cosmos to know itself." The electron volt became one of the tools that allowed that knowing to happen. But this shift points toward an even deeper mystery, one woven through modern physics. Once you express mass in electron volts, patterns emerge. Patterns in how particles relate. Patterns in how nature distributes mass. Patterns that suggest the universe may be far more finely arranged than it appears. And that leads us to the next frontier, a question waiting quietly beyond the numbers. If mass and energy share one language, why do some particles become so light they nearly vanish from existence? Part 4. Why is the neutrino so light that it took a century to prove it even has mass? Something almost unbelievable has been flowing through your body since the moment you were born. Particles so ghost-like that trillions pass through every square centimeter of your skin each second without leaving a trace. They travel through Earth as though it were empty space, cutting through oceans, mountains, metal everything without slowing down. These are neutrinos, nature's quietest travelers, and their near weightlessness became one of the greatest puzzles in modern physics. Their mass is less than 0.8 electron volts, a number so tiny that kilograms cannot express it meaningfully. To understand why the discovery took nearly a century, we must return to the beginning, to a moment when physics seemed to break in the 1920s. Nuclear scientists noticed something strange in beta decay. The emitted electrons didn't always carry the same energy. Something invisible was taking energy. A way to solve this. Wolfgang Pauli proposed a new particle so light and so weakly interacting that it would be almost impossible to detect. He wrote, half joking and half afraid, that he had done a terrible thing by suggesting a particle that might never be observed. Years later, Enrico Fermi built the first complete theory of this mysterious particle and gave it a name, the neutrino, the little neutral one. But naming it and detecting it were two entirely different challenges. A beam of neutrinos could pass through a block of lead 1,000 kilometers thick, and almost all of them would pass through untouched. That near invisibility defined the next century of experiments. The first confirmed detection came in the 1950s at the Savannah River nuclear reactor in the United States. Clyde Cowan and Frederick Rains used enormous tanks of water lined with light sensors, waiting for the rarest of events, a neutrino striking a proton. After years of painstaking work, tiny flashes of light confirmed that the neutrino was real. Rains later received the Nobel Prize for the discovery, but even then, nobody knew its mass. For decades, neutrinos were believed to be massless, a property built into the Standard Model, simply because no experiment could detect even a hint of mass. But the universe had left clues in the heart of the sun. Solar models predicted a certain number of neutrinos reaching Earth each second. Yet in the 1960s, the Homestake experiment detected only 1/3 of the expected number. This became the solar neutrino problem, one of the greatest astrophysical mysteries of the century. The solution came decades later, when massive underground detectors in Japan and Canada recorded something astonishing. Neutrinos were changing identity mid-journey. This behavior, neutrino oscillation, can only happen if neutrinos have mass. Tak, AKI, Kajita, in Japan, and Arthur B. MacDonald in Canada revealed this experimentally, earning the 2015 Nobel Prize in Physics. Their detectors Super Kamiokande and SNO were vast observatories filled with ultra-pure water and heavy water, shielded beneath mountains. They captured faint rings of blue Cherenkov light, revealing the types of neutrinos arriving from the sun. When those rings showed that neutrinos were shifting between flavors, the conclusion was unavoidable. Neutrinos have mass. The scientific world was shaken. As Leon Lederman once said, the universe is not only stranger than we suppose, but stranger than we can suppose. Neutrinos proved that again. But how small is their mass? Less than 1 eV. An electron is 0.511 million electron volts. A proton is 938 million electron volts. A top quark reaches 172 billion electron volts. A neutrino is lighter than a single electron volt. That means a neutrino could be 500 times lighter than an electron, possibly even lighter than we can currently measure. Yet, the universe is filled with them. Trillions of neutrinos pass through your body every second. Supernova explosions unleash unimaginable floods of them, so many that detectors like Super Kamiokande in Japan have captured bursts from stellar events thousands of light years away. NASA's Ice Cube Observatory in Antarctica now detects high energy neutrinos arriving from galaxies billions of light years beyond our own. Using a cubic kilometer of crystal clear Antarctic ice as a natural detector, each captured neutrino becomes a message from a cosmic event too distant or too energetic to study by any other means. These detections reveal something deeper. Neutrinos are everywhere. They form a cosmic background that fills all of space with silent motion. According to current calculations, there are roughly 336 neutrinos per cubic centimeter of space relics left over from the Big Bang itself. They travel at nearly the speed of light, carrying information from the universe's earliest moments, yet remain almost impossible to weigh. Their lightness forces physicists to confront a profound question. Why are neutrinos so incredibly light compared to every other particle? This mystery inspired new theories. One, called the seesaw mechanism, proposes that neutrinos may hide a heavy counterpart to right-handed neutrinos so massive that it lies far beyond the reach of modern experiments. The feather-light neutrinos we detect would then be the faint echoes of this unseen, enormous partner. Other ideas suggest that neutrino masses emerged during the earliest instants of the universe, when fundamental symmetries shattered as the cosmos cooled. These possibilities connect particle physics with cosmology, tying the smallest scales to the largest. ESA's Planck mission, which mapped the cosmic microwave background with breathtaking precision, placed strict limits on how much neutrinos can influence cosmic structure. Their tiny masses affect how galaxies form, how clusters grow, and how matter clumps across billions of years. Even something as light as a neutrino has shaped the universe. But perhaps the most striking achievement is the experiment that finally placed a direct upper limit on neutrino mass. The Katrina experiment in Germany studied the energy of electrons produced in tritium decay. By measuring these electrons with astonishing precision within a tiny fraction of an electron volt Katrina, showed that the neutrino's mass must be less than 0.8 electron volts. After decades of effort, this confirmed that neutrinos are not massless. They simply sit at the faintest edge of the measurable dot in a universe filled with massive stars, dense planets, and heavy atoms. The neutrino remains a whisper, the quietest trace of matter we know. Its discovery reshaped entire fields of science, overturning long-held assumptions and revealing the delicate fabric of the universe at its smallest scales. But a deeper mystery sits behind this discovery. If the neutrino is so light, then why do other particles carry such dramatically different masses? Some hundreds of thousands of times heavier, some billions of times heavier. This contrast leads to the next question. Part 5. Why does the electron weigh 500,000 times more than a neutrino? The first shock lies in the numbers. The electron weighs about 500,000 times more than a neutrino. Even though both belong to the same quantum family, this imbalance is so extreme that it challenges intuition, forcing us to examine why nature assigns such specific masses to the particles that build all visible matter. To understand this, we begin with the electron, the particle that anchors atoms, stabilizes chemistry, and determines nearly every structure you can see. Its mass, about 0.511 MeV/c², is tiny in everyday terms, but enormous compared to the feather-light neutrino. Without this mass, electrons wouldn't orbit nuclei. Atoms wouldn't exist. Stable matter would collapse into a haze of unbound particles. And yet, despite its central role, we still don't know why the electron has this precise mass. The Standard Model explains how mass arises through interaction with the Higgs field. Particles interact with the Higgs field differently, and those interaction strengths determine their masses. But the model doesn't explain why those strengths have the values we measure. It only records them. This uncertainty becomes sharper when comparing the electron with the neutrino. Neutrinos weigh less than 1 electron volt so light that early experiments mistakenly declared them massless. Their discovery took nearly a century. From the early hints in beta decay to the massive underground detectors that finally caught them in the act. Even today, experiments like Katrin have only set upper limits. Rather than measuring an exact mass, this contrast is stable. Well-defined electron mass versus a neutrino, so light it almost vanishes, forms the core of the mass hierarchy puzzle. The story deepens when we look at how the electron's mass was discovered in the late 19th century. J.J. Thomson used cathode ray experiments to determine the ratio of the electron's charge to its mass. Later, Robert Millikan's oil drop experiment measured the electron's charge precisely. Combining the two values produced the first accurate measurement of the electron's mass, a particle so light, yet so essential. As NASA and ESA missions studied interstellar gas and stellar atmospheres, the electron's mass became a fundamental ingredient. Electrons jumping between energy levels in hydrogen produce spectral lines features used by telescopes like Hubble, JWST, and ESAS Gaia to decode the composition of stars and galaxies. The electron is not just a particle. It is a cosmic measuring device. Neutrinos, in contrast, leave almost no trace. They seldom interact, passing through the entire Earth as if it were empty space. Detectors like Super Kamiokande and IceQ required immense ingenuity to isolate their faint signals, and yet their tiny mass subtly shapes the universe. ESA's Planck mission showed that neutrinos influenced how galaxies and clusters formed by streaming rapidly in the early cosmos and smoothing out density fluctuations. The contrast becomes even more intriguing when we consider that the electron is not heavy by human standards. Its mass is so tiny we never feel it. Yet compared to the neutrino, the electron is a heavyweight anchor that stabilizes matter. To explain this difference, physicists examine how particles interact with the Higgs field. The electron couples strongly enough to gain a stable mass. The neutrino interacts so weakly that its mass slips to the edge of detectability, but no final answer exists. We have the equations describing the pattern, but the deeper origin of these masses remains hidden. Some theories propose heavy, hidden right-handed neutrinos, accessible only at energies far beyond our current reach. In the seesaw mechanism, the observed neutrino mass becomes tiny precisely because its partner is enormous. If true, the mass gap between electron and neutrino contains clues about physics far beyond the Standard Model. Cosmic observations offer more insight. If neutrinos were heavier, ESA's Planck results show that galaxy formation would look different. Their small mass is written into the structure of the universe itself. NASA's study of neutrinos from supernova SN 1987A confirmed they travel. Just slightly slower than light, proof of their tiny but non-zero mass. Electrons build atoms. Neutrinos drift through the cosmos, whispering traces of the universe's earliest seconds. Electrons give stability. Neutrinos give subtlety. Together they reveal two extremes of nature's ability to assign mass. This imbalance hints that the rules selecting particle masses are far more complex than the standard model suggests. Even the Planck mass, towering far above both electron and neutrino masses, reflects this enormous hierarchy, a staircase with uneven steps, stretching from nearly zero to the highest energy scale nature allows. Why these numbers? Why this order? Experiments refine the measurements, but deeper origins remain hidden. Carl Sagan once said, "Somewhere, something incredible is waiting to be known." The electron-neutrino mass contrast is another sign that physics hasn't yet uncovered every layer of reality. And once we step inside protons and neutrons, the particles that form the nuclei of atoms, the puzzle deepens even further, because the building blocks inside, the quarks, are heavier than electrons, yet still far too light to explain the proton's mass. You begin by imagining something almost impossible, a force in nature that does the opposite of what your intuition expects. As quarks drift apart, the strong force doesn't weaken. It tightens, drawing them back with rising intensity, like a spring whose tension increases the more it is stretched. That tension holds energy, and in the quiet language of physics, stored energy becomes mass. So the substance of a proton comes, not from the quarks themselves, but from the energy swirling between them. Only when experiments became exquisitely precise did this strange truth come into focus. You picture researchers at Jefferson Lab in the United States mapping how quarks share their momentum inside a proton. Their results revealed that quarks carry only part of the internal motion. Gluons and the invisible fields that bind them carry the rest, forming the dominant contribution. Across the world, experiments at Desweiler in Germany confirmed this picture. When high-energy electrons collide with protons, the proton responds not as three tiny particles, but as a dense, restless landscape of gluon activity. To understand this realm more deeply, physicists built a computational method called lattice quantum chromodynamics. You imagine space divided into tiny cubes, each one holding calculations of quark and gluon behavior. Supercomputers run thousands of simultaneous processes to simulate the strong force on this grid. Yet from these vast calculations comes one elegant result. Even when the quarks are assigned very small masses, the proton still appears with the correct weight. The mass comes from confinement energy, not from the quarks themselves. So every atom you touch, every object you lift, gains its weight from the motion and fills inside protons and neutrons. The quarks are like seeds, but the storm of energy around them supplies nearly all the mass. This conclusion reaches far beyond the laboratory. NASA's studies of neutron stars depend on the same physics. A neutron star is a colossal version of atomic matter, so dense that a teaspoon of it would outweigh mountains. Its stability relies on how quarks and gluons behave when squeezed to unimaginable pressures. Their behavior in these stars confirms that the strong force provides the majority of internal pressure and mass, just as it does inside protons here on Earth. Cosmology adds its own confirmation. The Planck mission mapped faint light from their early universe and revealed how ordinary matter gathered into clumps. These patterns depend directly on proton mass. If proton mass were mostly from quark mass, the structure of the cosmos would look different. Instead, the observed patterns match predictions of quantum chromodynamics, showing that confinement energy shaped the formation of galaxies. Even the first elements forged after the Big Bang carry the signature of this process. As the universe cooled and protons and neutrons fused, the strength of the strong force determined what elements formed and in what amounts. Measurements of primordial helium by NASA and ESA match the predicted values that rely on proton mass from confinement, not from quark mass. The universe's early chemistry confirms this hidden source of mass inside every proton. Virtual particles flicker into existence and vanish. Quark-antique work. Pairs and gluon fluctuations that persist only for fractions of a second. Though brief, they add to the internal energy and therefore to the proton's mass. These effects leave measurable imprints in particle jets at CERN's Large Hadron Collider and appear in scattering experiments around the world. A puzzle that once seemed unsolvable, how quarks lighter than electrons could form heavy protons, now fits together. The proton's mass is not the weight of its ingredients, but the weight of the interaction holding them. The strong force creates such intense confined motion that it generates almost all the mass in ordinary matter. Quarks give the structure. The energy between them provides the substance. Carl Sagan once said that something incredible waits to be known. Inside the proton, that incredible thing turned out to be the origin of mass itself, not hidden in particles, but in the energy that binds them together. And now, as you settle into this realization, a gentler understanding emerges. Everything familiar, your atoms, your body, the objects around you, is built not from quark mass, but from energy held in place by the strong force. It leaves you with a natural curiosity. If nearly all of your weight comes from energy, what does that mean for matter itself? Part 7. The surprise arrives quietly. About 99% of your body's mass comes from something with no mass at all. The quarks inside your protons and neutrons contribute only a tiny fraction of your weight. The rest, almost all of it, comes from the binding energy of the strong force. It is one of the most counterintuitive insights in physics, a discovery that reshaped our understanding of matter and revealed what your atoms are truly made of. A proton holds 3 quarks, 2 up, 1 down, yet their combined masses reach only about 1% of the proton's total. The remaining 99% arises from the motion, tension, and energy of the gluons linking them. Quantum chromodynamics explains this storm of activity. Inside a proton, quarks exchange gluons at extreme speeds, creating a sea of motion so intense that energy becomes almost the entire mass. Murray Gell-Mann once remarked that mass is simply energy stored in motion. Inside the proton, this idea becomes literal. The quarks weigh almost nothing. The motion around them creates the weight you feel. This picture unfolded slowly. In the 1960s, deep inelastic scattering experiments at SLAC fired energetic electrons at protons and discovered not only the quarks, but additional energy too large to ignore. This energy came from gluons, the carriers of the strong force. Attempts to pull quarks apart only add energy, which then creates new particles, ensuring quarks remain confined. The proton is not a quiet structure, but a dynamic environment where motion never stops. Experiments at Desi, Jefferson Lab, and CERN made this clearer. The proton is not a simple container of 3 quarks, but a swirling field of quarks, gluons, and virtual particles flickering in and out of existence. Together, they form the mass of your body. Nearly every gram you can measure comes from this constant internal motion. Neutron stars reveal the same truth on cosmic scales. These stellar remnants, essentially enormous collections of neutrons, owe their structure to the strong force. NASA's NICE mission measured their sizes and densities and confirmed that this force provides most of the mass in both stars and ordinary matter. Cosmology echoes the same conclusion. The Planck satellite revealed patterns of matter in the early universe that depend on proton mass. Because that mass comes from confinement energy, the universe formed as it did. Galaxies clustered the way they should. Stars ignited the way they had to. Even the first elements depended on this mass. Measurements of primordial helium by NASA and ESA matched the values predicted using QC-derived proton and neutron masses. If those masses had been different, the universe's earliest chemistry would have changed, possibly preventing stars from forming at all. To understand this intuitively, you picture the proton as a region of tightly bound energy. The quarks act as anchors, while the gluons create an elastic field around them. Stretching this field stores energy, and that energy becomes the proton's mass. This is why isolated quarks are never found. The strong force increases as they separate. Energy pumped into the system simply creates new particles, keeping quarks forever confined. This confined motion is the energy you carry every moment. Lattice QCD made this story precise. When physicists simulated the proton on a grid and even set quark masses extremely small, the proton's mass still emerged correctly. It came from interactions and motion, not from the quarks themselves. The match to experimental values was exact. It confirmed that your body, your world, the planets and stars you see, are made from energy compressed by the strong force. Carl Sagan reminded us that we are a way for the universe to know itself. Through QCD, the universe reveals that the matter in your body is structured motion energy, held in place for billions of years. But this understanding opens the door to another wonder. If almost all your mass comes from binding energy, what happens when quarks become so heavy that the strong force can't confine them? Part 8. You drift to the edge of the particle world and encounter a final surprise. The heaviest quarks are so massive that nature cannot hold them. The top quark, weighing more than entire atoms, vanishes almost the moment it appears, lasting only about 10 seconds. Too heavy to bind, too brief to form matter, it flickers in and out like a passing thought before the strong force ever has a chance to act, a lifetime so brief that even the strong force cannot embrace it. A flicker of existence appearing inside the chambers of CERN and Fermilab, only to dissolve into lighter particles before the universe can decide what to do with it. To understand why, you step slowly into one of the most extreme corners of physics. A realm where mass grows so large that the familiar rules of matter begin to slip away. The story traces back to the 1990s, when the Tevatron accelerator finally uncovered the top quark. Researchers had expected it to be heavy, but its measured mass stunned them, greater than an entire gold atom, contained inside a single elementary particle. Its deep connection to the Higgs field made it the strongest coupled and, in turn, the most fleeting particle ever observed. To sense that lifetime, imagine the strong force acting inside protons and neutrons. Quarks feel a constant pull that drags them back together, a confinement so quick and powerful that they become trapped almost instantly. But the top quark slips away before this can happen. It decays faster than gluons can begin weaving those bonds, faster than the strong force can shape it into anything stable. And that is why nothing in the universe is built from top quarks. They vanish before structure can form. Its decay is ruled by the weak interaction, the process that lets particles transform into others. The heavier the particle, the more tightly it couples to the Higgs field, and the faster the weak force unravels it. For the top quark, the unraveling is immediate. The strong force never even arrives. This rare, fragile moment gives physicists a unique gift. Because the top quark decays before confinement clouds it with binding energy, its properties reach detectors almost untouched. Every other quark is wrapped in the turbulence of the strong force. The top quark alone appears in something close to a pure state. Fermilab and the Large Hadron Collider have captured these fleeting traces with remarkable precision. From the brief patterns in their detectors, scientists reconstruct the instant. A top quark existed, each event a direct imprint of the particle itself. This strange behavior leads to deeper questions. As mass increases, interaction with the Higgs field strengthens dramatically. Decay accelerates. Lifetimes shrink. The top quark sits near the point where this coupling grows so intense that nature refuses to let the particle remain whole. Yet, it hints at something more. Its enormous mass lays it only a few steps below the scale where gravity and quantum mechanics begin to blur. The energy range where new layers of physics might wait. Though far from the Planck mass, the top quark's behavior feels like a whisper of the frontier where space-time begins to resemble the shifting, foamy landscape John Wheeler once described. To see the decay itself, imagine the top quark transforming into a bottom quark and a W boson. Inside detectors, this becomes a spray of jets, leptons, and neutrinos. Because no hadrons form around it, those patterns arrive unusually clean, offering one of the sharpest tests of the Higgs mechanism. Its mass, its interactions, its timing all reveal whether the standard model holds steady or if faint cracks signal something deeper. Telescopes in orbit, NASA and ESA observatories never detect top quarks directly. Their lives are too short. But the universe they observe tells the same story. Galaxies, black hole accretion flows, and the cosmic microwave background all depend on long-lived lighter quarks. If top quarks had survived even slightly longer in the early universe, matter might have formed in an entirely different way. Their absence shaped everything by simply not participating. They appeared only in the first brilliant moments after the Big Bang, and now only in the hottest collisions we create, always vanishing before they can become part of anything. When the Tevatron confirmed the top quark in 1995, the discovery carried its own quiet emotion, a triumph decades in the making. Its mass had been inferred through careful theory, but watching it appear and then fade in less than 10 seconds revealed how thin the boundary is between the particles that build our world and those that exist beyond stability. Carl Sagan once said, "Somewhere, something incredible is waiting to be known." The top quark is one of those incredible things, a reminder that nature holds particles so heavy and unstable that they cannot remain long enough to shape matter. Yet, still brush against the edge of deeper frontiers, and that leads to a further boundary. If a particle can become so massive that even the strong force cannot hold it, what lies beyond? What happens when mass climbs to the point where gravity begins to challenge quantum forces? This brings you to the threshold marked by the Planck. Mass, the point where a single particle becomes a microscopic black hole. The numbers appear ordinary. About 2.176 times 10 kilograms. But in particle physics terms, this corresponds to nearly 10 gigaelectron volts. An energy so immense that gravity itself becomes strong enough to seal a particle inside its own horizon. At this razor edge, collapse happens instantly. Shrink mass into smaller and smaller regions, and gravity intensifies because the mass occupies less space. At everyday scales, this growth is gentle, but as you near the Planck length, about 1.616 times 10 meters, gravity suddenly surges at exactly one mass value. The Schwarzschild radius becomes equal to the Planck length. At that point, the particle stops behaving like a particle and becomes a tiny black hole. This insight emerged by merging Einstein's picture of gravitational collapse with quantum limits on measurement. The mass required to create a horizon the size of the smallest meaningful distance matched the Planck mass precisely, suggesting a natural boundary, a point where space-time cannot support anything heavier without folding inward immediately. The roots of this idea stretch back more than a century. Einstein showed that enough mass in a small region traps even light. Quantum theory revealed that confining a particle tightly boosts its energy. Max Planck later introduced natural units built from the constants of nature, the speed of light, Newton's gravitational constant, and the reduced Planck constant. Only later did physicists realize these units mapped the boundary where quantum mechanics and gravity directly collide. As research advanced, the meaning became clear. If mass ever reaches the Planck value inside the Planck length, its energy curves space-time so sharply that a tiny gravitational well forms around it. Asterisk observations of black holes, studies of gravitational lensing, and solutions to Einstein's equations all echo the same relationship between mass, curvature, and horizon. Scaling those relationships downward reveals something unexpected. The very same equations predict gravitational collapse, even on microscopic scales. This shifts how you think about particles entirely. In quantum mechanics, a particle spreads across a region described by its wave function. The tighter you try to confine it, the more energy you pour into that shrinking space. But if that energy ever surpasses the Planck mass while confined within the Planck length, space-time gives way before the wave function can contract any further. The wave function does not fail, space itself does. This helps explain why no particle we know approaches such a mass. The top quark, the heaviest in the Standard Model, rests near 172 gigaelectron volts, still 17 orders of magnitude beneath the Planck scale. Even the speculative particles dreamed up by supersymmetry or grand unified theories fall far below this boundary. It is as though nature prevents anything from reaching that mass, because gravity would intervene instantly. Experiments reinforce this idea indirectly. Even at its full power, the Large Hadron Collider launches protons to around 7 teraelectron volts, immense by human standards, yet tiny compared to the Planck energy. Head-on collisions between these protons never come close to forming a Planck-scale object. If one appeared, the detectors would record a distinctive pattern, a brief storm of decay products, or perhaps a stable remnant. No such signature has ever surfaced. Cosmic rays, however, venture far beyond what our machines can reach. Some plunge into Earth's atmosphere with energies above 10 gigaelectronvolts, carrying more power than any collision humans have ever created. And still, even these rare events do not generate Planck-mass particles. The universe stays faithful to the boundary. Another clue comes from black hole evaporation. Hawking's calculation shows that black holes shed energy, and the smaller they are, the faster they disappear. A black hole weighing the Planck mass would radiate away its energy almost instantaneously, flashing out of existence as soon as it forms. This makes the Planck mass not just the threshold where collapse begins, but the lowest mass at which a black hole can meaningfully exist at all. Below that, the notion of a horizon dissolves. At this scale, space-time itself becomes turbulent. At large distances, it appears smooth and geometric. But near the Planck length, quantum fluctuations twist it so violently that space-time resembles a churning, restless medium. John Wheeler called this quantum foam, a poetic image for a geometry unable to stay still even for an instant. In this extreme regime, the distinction between matter and space blurs. Multiple theoretical frameworks try to describe what lies here. String theory imagines particles as minuscule vibrating loops, whose natural tension aligns with the Planck scale. Loop quantum gravity breaks space-time into discrete geometric units, making the Planck mass the point where these units become unavoidable. Causal dynamical triangulations rebuild space-time from simple blocks, and the Planck mass marks the curvature limit of their shapes. Though these theories differ deeply, they converge on the same truth. The Planck mass is the place where geometry turns quantum. Astronomy echoes this idea from afar. The James Webb Space Telescope uncovers ancient galaxies, whose shapes trace fluctuations seeded at energies close to this frontier. The Planck satellite mapped fine variations in the cosmic microwave background, patterns created when early universe quantum effects were stretched across the growing cosmos. These observations show that the universe itself once passed through energies where quantum gravity reigned completely. Across theory, experiment, and cosmology, the Planck mass stands as a boundary. It is the mass where gravity and quantum rules weigh equally. The mass where relativity smooths space-time fractures into turbulence. The mass where particles stop acting like particles and begin acting like pure geometry. And now, after following this thread through collapsing regions, through the physics of the early universe, and through the strange edge where forces merge, one quiet question drifts into view. If the Planck mass is the point every theory must cross, why does every attempt to unify physics return to this same silent value? Part 10. Why is the Planck mass the gatekeeper of quantum gravity? Something extraordinary waits at the boundary of known physics, a mass so unusual that every unifying theory eventually circles back to it. The Planck mass, around 2.176 times 10 kilograms, seems tiny to our everyday senses, yet in particle terms, it carries an energy so immense that quantum mechanics and gravity collide directly. It marks the territory where no single framework can stand alone. Einstein's relativity strains, quantum rules lose their clarity, and the very structure of space-time must be rebuilt from its foundations. This boundary arises from a simple observation. At ordinary scales, gravity is astonishingly weak. A small magnet can lift a paperclip against an entire planet, but as mass is compressed into smaller regions, gravity strengthens quickly. If a particle becomes both heavy enough and compact enough, gravity overtakes every other force and folds the particle inside its own horizon. When theorists calculate the mass for which this collapse happens at the precise size of the Planck length, the value that emerges is the Planck mass. Nothing lighter can be squeezed that tightly. Nothing heavier can avoid collapse. This surprising threshold reveals a deeper insight. At the Planck scale, gravity becomes as strong as the other fundamental forces. Normally, these forces differ enormously. The strong force binds quarks with tremendous strength. Electromagnetism shapes atoms and chemistry. The weak force governs transformations, and gravity barely murmurs in comparison. But at the Planck mass, that hierarchy breaks. The forces meet. Wheeler's image of space-time as a frothing, restless surface is not mere metaphor. At these energies, fluctuations become so large that space-time shakes and jumps, losing the smoothness described by relativity. To imagine this, picture shrinking a particle to the smallest length quantum gravity allows. At that size, any attempt to measure its position injects tremendous energy into the region. Relativity says this energy curves space-time. With enough curvature, the region collapses into a tiny black hole. The very act of measurement destroys the particle's identity below the Planck scale. The familiar language of physics breaks down. Quantum mechanics and gravity undermine each other. This is why the Planck mass becomes the gatekeeper. Any unified theory must function here, or it cannot describe the universe fully. String theory reaches this boundary with vibrating loops. Loop quantum gravity approaches it through quantized geometry. Causal dynamical triangulations assemble spacetime from simple shapes. Though vastly different, each theory must embrace the Planck mass as the transition where classical spacetime dissolves into quantum structure. Cosmology reinforces this again. NASA and ESA's studies of the early universe show delicate temperature patterns in the microwave background, patterns born from ancient quantum fluctuations, magnified during cosmic inflation. Their shapes reflect processes that occurred just below the Planck scale. Any higher, and those fluctuations would have collapsed into microscopic black holes. Instead of stretching into galaxies, black hole physics also bends toward this boundary. Hawking radiation intensifies as black holes shrink. A black hole near the Planck mass would evaporate faster than it forms, a final expression of the tension between gravity and quantum rules. The energies of the Large Hadron Collider lie far below this scale, around 10 GeV, compared to 10 for the Planck mass. No human machine will reach it. Yet the early universe did, and its echoes remain in the structures JWST now observes. When physicists face this boundary, they confront the limits of both of our great theories. General relativity predicts collapse. Quantum mechanics predicts violent uncertainty at the Planck mass. Their languages contradict each other completely. Even hypothetical Planck mass particles behave unlike anything known. Their Schwarzschild radius matches the Planck length exactly, a sign that gravity and quantum rules converge with perfect symmetry. Some researchers wonder whether the most extreme cosmic rays might graze this frontier, though they still fall many orders short. Even so, they hint that nature occasionally steps toward the foothills of quantum gravity. The Planck mass defines the energy where unity becomes unavoidable. Any true theory of everything must explain why gravity is nearly silent at low. Energies yet becomes dominant at this threshold. It must connect quantum interactions and the curvature of spacetime without contradiction. Every modern framework, string theory, loop quantum gravity, emergent spacetime models, holographic ideas, must pass this test. If it fails here, it cannot describe nature. The Planck mass holds a quiet authority. It is not a particle, not an object, not something you can detect. It is a threshold, a lighthouse at the edge of an uncharted sea, showing only the limit, not what lies beyond. Carl Sagan once said, "Somewhere, something incredible is waiting to be known." The Planck mass is one of those waiting places, a silent number holding the unanswered questions of quantum gravity behind it. Whatever the ultimate theory becomes, whatever space-time turns into when it bends and reforms, the road toward understanding passes through this mass. And now, after moving from quarks to horizons, from binding forces to microscopic black holes, from the early cosmos to the edge of space-time itself, you arrive at the gentle end of this exploration. Thank you for sharing this quiet stretch of the night with me. If this slow journey through physics gave you even a moment of calm, I'm grateful our paths crossed. If you choose to like or subscribe, it softly encourages me to continue shaping these late-night wanderings. And if you feel comfortable, I'd love to know where you're listening from or which part of this story lingered with you. Your messages, small or long, guide me in ways you may not expect. As you settle into rest, may the stillness around you soften every remaining thought.